Welcome to the Ultimate Physics channel. The topic of this video is solving problems on time dilation. We know that time dilation is one of the fundamental effects of the special theory of relativity. Let us do a quick recap of the concept of time dilation before we solve some problems on the topic. So, time dilation refers to the effect where a moving clock ticks more slowly than a clock at rest. Measurements of time intervals are affected by relative motion between the observer and what is observed. So the expression for time dilation is given here. That is, if an observer in a frame of reference S is measuring a time interval del t, he will always measure a dilated time del t prime for a clock that moves at a relative velocity u with respect to his own frame of reference, which is given by this equation. Del t prime is equal to del t over square root of 1 minus u squared over c squared. Here I have used the notation del t prime and del t. You could very well use t prime and t. Because it is an interval of time anyway, I have used a delta there, where del t and del t prime are the proper time and the dilated time respectively as measured by an observer in S frame of reference moving with the relative velocity u with respect to another frame of reference S prime fixed to the clock on which del t prime is measured. C is the speed of light in vacuum, we know that. It is important to note that an observer in S prime frame does not realize any dilation in his own clock, whereas the observer in S frame measures the dilation for the same clock carried by the observer in S prime. That is the important point to note here. That means the long intervals between the ticks for him. That is, the clock has really slowed down. It is also worthwhile to remember that all the biological processes of the moving observer slow down. So it is not just clocks that are affected, the time itself is affected, which has been clearly established by special theory of relativity. Now with that ideas in mind, with those ideas in mind, let us move on to solve some problems on the topic of time dilation. The first problem, an athlete who is aware of special relativity and the concept of time dilation decides to set a 100-meter dash record by getting the time for the 100-meter dash measured from a moving frame aboard a spaceship, hoping that time dilation would help her set a world record. Is this a good idea? One can assume, for example, in a 100-meter dash, if she is capable of, let us say, finishing the dash in about, let's say, 10 or 12 seconds. On Earth, she is thinking that since time would be dilated for an observer on a spaceship, if she requests the referee to be aboard a spaceship and measure the event on Earth, where she runs the race or the dash, 100-meter dash, she is thinking that time dilation would help her. Is this a good idea? It is absolutely not a good idea at all. Why? There are two reasons that I can list out as to why this is not a good idea. The first one is the fact that from the spaceship, all clocks on Earth slow down because Earth is in relative motion with respect to the spaceship. So if the spaceship is moving at a velocity u, it is according to the spaceship, or for an observer on the spaceship, let us say the referee is sitting there on the spaceship. For him, Earth is moving with a velocity minus u on the opposite direction, and therefore all clocks on the Earth slow down for him. That includes all biological processes on the Earth. Therefore, the referee on the spaceship would observe that all the event, the 100-meter dash and everything has slowed down on the Earth. In fact, he would see the action of the 100-meter dash in slow motion from the spaceship. So definitely, according to the observer on the spaceship, that is the referee in this case, time has slowed down on the Earth, and therefore the 100-meter dash would take a longer time than it does on the Earth, because a clock on the spaceship is going to be used, let us say, for this thing. Though the clock may not slow down actually, he would see that the process itself is taking a longer time here from the spaceship if he measures. So that is one reason why it is definitely not a good idea. But there is another important reason as well. That is second reason that I'm uh, listing out here. That is the time taken for signals to travel from Earth to the spaceship, because there must be a way for the uh, uh, referee to know the event has started, that is the 100-meter dash has started, and when it has started, and of course when it ends, you must know that it has ended. So the start and the finish of the 100-meter dash, let us say, are indicated to him by probably firing some kind of a gun or light flash or something on the Earth, which he can observe from the spaceship while going. So he will definitely realize that the signal has been indicated, but the problem is that would take a definite time to travel. Light signal is the fastest signal one could send, and even that light signal would take definite time to reach the spaceship, and that will depend on the distance between the Earth and the spaceship. And as the spaceship is moving with constant speed, it is definitely going to take a long time to reach the spaceship. And similarly, when the event ends, other signal will indicate that it has ended. So that also will take some additional time. So 2 times that signal time also is important for it. Will be added to the event time. So event time, he measures a dilated time. Additionally, signal time is there. So put together, that becomes the total time for the event according to him. And that is going to be definitely longer, the total time taken for the event. So on these two counts, one could clearly therefore see that it is not at all a good idea uh, by the athlete to have her performance measured or assessed by a referee or board a spaceship. That is the conclusion we can arrive at. I'll just put those things that I discussed now here. Yes, let's move on to the next problem. An athlete who runs 10 meters per second completes a 100-meter dash, right? She competes in a 100-meter dash rather. How much time her watch gains or loses during the dash? That is the question now. Now the question is, this is in this case very a small amount of time that the watch would gain, because the race is she's running is only at 10 meters per second speed, but nevertheless there will definitely be some time gained by her watch. So let us try to write a solution for this. Right. So the athlete is carrying a small watch, and this watch also is expected to have a time dilation, because it is traveling with the athlete at 10 meters per second speed compared to the stationary Earth. Of course, the athlete is running the race on the Earth only, but it is also a moving clock with respect to a stationary clock on Earth. So if let us take the time on the Earth as t0, and let us say 1 second is the time, right? 1 second. Now this is 1 second interval. Let us just think. It is 10 meters per second, 100-meter dash. So it will take how much time? It will take 10 seconds. So let us just make this as 10 seconds for the race as counted by this thing. So I can now say that I am measuring a time interval that is equal to 10 seconds. Now the dilated time measured on the moving watch carried by the athlete is going to be given by this equation: 1 minus u squared over c squared. Right, now u is what? U is just 10 meters per second. It's not a very high speed or relativistic speed, so to say. But u over c, if you have to calculate, um, you can calculate by taking this one. It is 10 over 3 into 10 power 8. That is, this is 10 power 7. So this is 1 over 3, right? So 0.233 into 10 power minus 7, or 3.3 into 10 power minus 8 is the u over c in this case. So now here, if you substitute that, one can get this thing, but we can expand this a different way as well. Del t, let us say, is the time for the event, which is 10. This can be binomially expanded, right? So I'm trying to take it to the numerator and work out the binomial expansion of this. That is 1 minus x power n is equal to 1 plus nx, right? This is the binomial expansion for this one. So I can say 1 plus u squared over 2c squared. Of course, additional terms are not significant, so we are ignoring those terms in the expansion of this one. So now we can say that this is equal to 10 into 1 plus u is 10 again. So 10 squared is written here. And then in the denominator, we would have 2c squared. So 2 into 9 into 10 power 16, because we have c as 3 into 10 power 8. C squared is 9 into 10 power 16. So that is equal to 10 into 1 plus 1 by 18 into 10 power minus 14. This one cancels, so 10 power minus 14 comes to the numerator. This is 1 over 2 into 9, that is 1 over 18. And that would be 1 plus 0 0, let's say some 3 digits I'm taking, 3 into 10 power minus 14, right? Okay, sorry, I can continue here probably, right? So in this case, therefore the time, dilated time, is equal to 10 plus this one is multiplying inside, so it is a point 555 into 10 power minus 14 seconds. So how much time does the watch gain? The watch gains about, I can say this term alone is 5.55 into 10 power minus 15, right? So this is 5.55 femtoseconds, so to say, right? So I can write femtoseconds, fs. So that is the total time gained by the watch carried by the athlete during the entire event. Because it is taking 10 seconds for each second, I can say that for each second, the watch would take an additional 0.55 femtoseconds. femtoseconds, right? An additional 0.555 femtoseconds for each second. So totally 10 seconds, there are 5.55 femtoseconds added to the watch carried by the athlete. That is the conclusion we can arrive at. Right. Now the third problem is a clock aboard a spaceship moving at the speed of 0.700 c relative to the Earth measures that a car takes about 40 minutes for a trip on Earth. What time interval would the driver of the car measure between the same two events? So we have a car on the Earth and that is taking 40 minutes for a trip. So what time the driver on the aboard the spaceship will take to for the same event? Here the question is, a clock on Earth measures some time which we don't know. But from a spaceship, when this event is recorded, this trip is recorded, this clock on the spaceship measures 40 minutes for the event, right? So that is not proper time, right? What is measured is dilated time. Therefore, I can say that del t prime in this case is 40 minutes. Therefore, del t is equal to del t prime multiplied by 1 minus u squared over c squared, where u is 0.700 c given in the question, and therefore our del t would be equal to, this is 40, so 40 times the square root of 1 minus 0.7 c squared and c squared will cancel. You have 0.79 is 0.49, that would be 40 into square root of 0.51, which if we do, we get 40 into 0.714, that would be 28.56 minutes. So the trip would take only about 28.56 as measured by the driver of the car, whereas on the spaceship, because of the dilation of this clock as observed by the observer on the spaceship, that trip would take 40 minutes. That is the conclusion we can give. Right, let's move on to the next one. An observer on Earth and aboard a spaceship set their clocks to measure same time, right? They are synchronizing the clocks basically. Those clocks are set to same time. When the spaceship is about to start a journey, so this is when the spaceship is abreast of the Earth. If the spaceship moves at a speed of 2 into 10 power 8 meters per second, how much time must elapse for the Earth observer before the clocks differ by 1 second? So the clocks must differ by 1 second. So how much time would have elapsed on the Earth? That is the question here. Okay. And the speed of the spaceship u is given in this question as 2/3 of the speed of light, right? So 2 into 10 power 8 meters per second. So we can use time dilation expression, that is del t prime is equal to del t over square root of 1 minus u squared over c squared. For us, we need a difference, right? The difference must be 1 second. So we can say that del t prime minus del t on the left side, we're just adding a term minus del t here, is del t over square root of 1 minus u squared over c squared minus del t again on the right as well. So if I take the LCM here, 1 minus u squared c squared del t minus del t of square root of 1 minus u squared over c squared, right? And here del t prime minus del t. So left hand side is 1 second, this asked in the question. Right hand side, I say del t is common, I get 1 minus square root of 1 minus u squared over c squared by square root of 1 minus u squared over c squared. Right? So substituting for u in that case, or we can take this one first, this one, del t on the other side, right? Um, yeah, we can retain this one, del t prime minus del t, and take this del t out here, let's say. So I say del t prime minus del t over del t is equal to 1 minus square root of 1 minus u squared over c squared over square root of 1 minus u squared over c squared, right? We need del t, isn't it? Yeah. So right hand side we can first work out, because we know that u is 2 into 10 power 8 meters per second. So we can work that out first. That is going to be 1 minus, if you plug in this u here, you would get for the square root term 0.7454 over the denominator is square root of this, which is again 0.7454, right? So if this is worked out, we get 0.255, 0.745, and that would be equal to 0.342. So in this case, what we have is del t prime minus del t over del t is equal to 0.342. Therefore, del t is equal to del t prime minus del t over 342.342. This is equal to 1 over 0.342, because the difference has got to be 1 second. So therefore, finally we arrive at del t as 2.93 seconds. So when the clock on the Earth has measured 2.93 seconds, the difference between that clock and the clock on the spaceship would be 1 second. That is del t prime minus del t is 1 second. Of course, that tells us that del t prime is going to be 3.93 seconds. So that is the conclusion we can draw here. Okay, let's move to the next one. For an airplane moving at 300 meters per second, how much time must elapse before a clock on the airplane and the one on the ground differ by 1 second? So this is not a very high speed here. U is just 300 meters per second. 300 meters per second. Okay, and therefore again same thing that we can do here. U by c we can calculate first. 300 over 3 into 10 power 8 meters per second, 300 meters per second. That would be 10 power minus 6 is the ratio u over c. Now again the same expression that we used last time, we can continue to use that here as well. That is del t prime minus del t. Okay, del t prime minus del t over del t is equal to 1 minus square root of 1 minus u squared over c squared, square root of 1 minus u squared over c squared. This is exactly the expression that we arrived at in the previous problem, right? So here, following the same approach, we can do okay. So again, if you do the binomial expansion, or we can directly substitute u here, but the problem here is If you substitute u, it is 10 power minus 6 square, that becomes 10 power minus 12 here. Here c is a 9 into 10 power 16. So that is going to get very clumsy. So the best way to resolve that issue is to go for, again, binomial expansion of these two terms. That is using this formula 1 minus x power n is equal to 1 plus nx. Additional terms are ignored here as well. So if that is done here, del t prime del t minus del t over del t is on the left hand side. Right hand side we have minus, second term alone is a u squared over 2c squared after the binomial expansion. And for the left it is 1 plus u squared over 2c squared. Right? Because if I do the binomial expansion, 1 minus u squared over c squared power minus half I have. If I take it to the numerator, that means it is 1 plus u squared over 2c squared plus additional terms. These two terms are taken and put it here. For the numerator, on the other hand, there is a minus already, 1 minus something. So there is 1 minus 1 of u squared over 2c squared will be there, right? Because there is not a minus or there is a plus of here. Because the square root is on the numerator. If it is a plus of there, then the sign will be plus actually, but minus there is outside, so outside we have to take minus side here. In both cases, we have used binomial expansion to arrive at this one. Okay, so if you do that substitution, we would get minus 0.5, because there is a minus sign here, into 10 power minus 12 second, right? That is del t prime minus del t over del t. And del t prime minus del t is again asked as 1. So our del t therefore turns out to be, this comes here and this goes there. So it is 1 over 0.5 into 10 power minus 12 seconds. Here the minus sign is not any physical significance, does not carry any physical significance. So we can say that is 2 into 10 power 12 seconds, right? Because this is in the denominator here. That means it will take a long time for a clock on an airplane, which is speeding at 300 meters per second constantly with respect to the Earth, to have its clock, differ by 1 second compared to a clock on the Earth. It will take such a long time. Okay, so that is the conclusion we can arrive at based on the answer that we have got here. 2 into 10 power 12 seconds, you can calculate how many years that is. Right. The next question is, what is the speed of a spacecraft relative to the Earth if each day on it corresponds to 2 days on the Earth? So 2 Earth days. What would be the speed of such a spacecraft if dilation is so much, right? So we can say that again the time dilation equation comes to our rescue to solve this one simply. So del t prime over square root of 1 minus u squared over c squared is equal to del t. Here u is what is required. So we can just take that to the right side and bring the other to the left side. So the same equation can be rewritten as del t prime over del t is equal to square root of 1 minus u squared over c squared. In this case, the ratio is 1:2, right? So we can say that this particular term on the left hand side is 1/2. Because 1 day on the spacecraft is equal to 2 days on the Earth, so 1/2. The square root here is 1. 1 minus u squared, c squared will be retaken. Now if you square on both sides, this is 0.5. 0.5 squared is 0.25 on the left hand side. Right hand side is 1 minus u squared over c squared. And therefore u squared over c squared is equal to 0.75, 1 minus 0.25. So u is equal to 0.75 times c square root of 0.75. MC. That is equal to 0.866. So 0.866. That is the speed at which the spacecraft has to move relative to the Earth, so that a clock on it measures 1 day for each year, for 2 days for each 2 days on Earth. Right. Moving on to the next one. Right. The speed of Apollo 11 spacecraft that landed on the moon in 1969 was 1.08 into 10 power 4 meters per second relative to the Earth. For an observer, how dilated a day on the spacecraft would be compared to this Earth day. So Apollo 11 missions, you know, these measurements could be done, right? The watches or the clocks carried by the astronauts on aboard the Apollo 11 spacecraft could be compared to the ground-based clocks for these measurements, right? So these results are experimentally verifiable. It is not an imaginary thought experiment of some kind of relativity. No, it is a real experiment that was performed. So one can say that again the time dilation simple equation comes to a rescue here as well. Del t prime is equal to del t over square root of 1 minus u squared over c squared. In this case, u is given as 1.08 into 10 power 4 meters per second, and therefore we have to just plug in those numbers here, isn't it? So if we plug in these numbers, we get let us say 1 second that is just seeing how much a second is gaining on the spacecraft, right? So 1 over the square root of 1 minus this thing, do the squaring, I get a 0.1296 times 10 power minus 8, because I'm squaring and dividing by 9 into 10 power 16 for c square, then I get 10 power minus 8 on here. If I plug in these numbers even a simple calculator, I would get 1 over square root of 0.89 centimeters, right? And then 8 to enter. And therefore, if I exactly take the square root, I will get 1 over square root, or not, no square root, right? I'm getting rid of the square root by taking it. So I get 9 nines now. So if I take the inverse, right, of this, I get del t prime as 1.8 zeros followed by 1 second. So you can clearly see how much the clock has gained. The clock has gained about, this is if you do the calculator, it is not even 1 nanosecond. If you do the exact calculation, you would get this additional term, taking into account the last decimal securetely, about 0.65 nanoseconds. That is the gain of the clocks carried by the astronauts on the spaceship, the spacecraft that went to Apollo 11, on the Apollo 11 mission to the moon. Right. The next question is interesting, right? The lifetime of, because it is a direct evidence of time dilation practically, right? The lifetime of a certain elementary particle is 1 into 10 power minus 7 seconds when at rest. How far it can go at a speed of 0.99 c. Right, we know that when we see the elementary particle data, we know that some of these particles measured at the Earth's atmosphere, their numbers are too much disproportional to what is expected, right? More numbers are available for us compared to uh, uh, that muons, for example. I have posted a video on this channel on muon lifetime paradox. That why more number of muons are measured on the Earth, considering their decay time, I mean the lifetime, right? That is because of dilation that occurs for a lifetime of muons on Earth. So this problem is testing that idea. So we can say that uh, in this case, the speed is given as 0.99 c. Del t is equal to, because the lifetime here is measured from lab frame, I take it as del t. And this 10 power minus second is the muon lifetime measured in its frame, right? So this time is dilated for Earth frame, so I can very well take this as del t prime is del t over square root of, again, the same equation we can use, where del t is my this thing 1 into 10 power minus 7 seconds, because in its frame lifetime for the muon is less, whereas in Earth's frame its lifetime is more dilated, right? It's dilated. Therefore, we are able to measure more number of muons than expected on the Earth. So similarly here, this elementary particle's lifetime is 10 power minus 7 seconds in its frame. So on Earth, if we put this, we can get square root of 1 minus 0.99 squared, c squared and c squared cancel. So we have this. If we work out the math, that is going to be 10 power minus 7.1411. And therefore del t prime is going to be equal to 7.089 into 10 power minus 7 seconds. So that is each this thing, 10 power minus seconds becomes 7 times more for the muon. So that means for this, not muon actually, this is some elementary particle. So for this elementary particle, the lifetime dilates by 7 seconds in the lab frame. 7 seconds, 7 times. Lifetime increases by 7 times its actual lifetime. Now the question is not that actually, right? The question is how far can it go at 0.99 c after its creation? So for that we have to calculate the distance it can move. So distance moved by the elementary particle is equal to the speed of the elementary particle multiplied by its lifetime in the Earth's frame, or del t rather we have taken here, right? So it is u times del t prime is equal to, this is the time we have calculated, right? So that one. 0.99 c, that is 0.99 into 3 into 10 power 8 multiplied by 7.089 into 10 power minus 7, and this will be the distance, right? This is 3 into 10 power 8, so this is the extra 10, so we get 210 meters if we work out, because this is roughly 3 into 7 is 21, 21, this is 10, so 210 meters is what we are getting for this one. So that is the distance this particular elementary particle would travel in its lifetime as measured in lab frame or Earth's frame, right? So the next one is, imagine space-time in the future. Sorry, imagine sometime in the future, a space agency wants to send astronauts to a nearby star that is 20 light years away. They decide that the round trip should take no longer than 40 years. Okay, so the round trip should take no longer than 40 years for the astronauts abroad. How fast must the spaceship travel, and how much time for the trip would the spaceship measure on Earth? Okay, so can we say about this problem? Here, obviously, some idea of length contraction is required, right, to solve this one. It is not a pure time dilation problem. Some amount of length contraction is missing here. So we say that length contraction idea is that proper length L naught gets contracted to L naught times the square root of 1 minus u squared over c squared, of course, which we generally call as the contracted length L, because of the moving, uh, the frame in which this length is measured is moving at a speed u. That is the idea of length contraction. So I give the expression here as, yeah. Now with that in mind, we can see that for the astronaut aboard the spaceship that he takes to this nearby star, um, his distance would also contract, right? So his distance is actually 20 years, just 20 light years distance he has for the nearby star. The return is another 20 light years, so total is 40 light years. So for the length contraction for the two-way trip for the astronaut, because he has to go and return back to Earth, hopefully. So two-way trip for the astronaut would be 40 times the square root of 1 minus u squared over c squared. Right. Now the question is here, what about the time dilation effects, right? For the clock aboard the spaceship, it should have counted 40 years max, right? Therefore, I can say that that clock would have dilated, so that is t prime is equal to 40 years. That means we can say that on Earth, t is measured on their clock, Earth clock. That would be t prime times square root of 1 minus u squared over c squared. Okay. Now, here the distance is getting corrected because of this length contraction. So we can say that the time, the measured time would be the distance taken for the journey over the velocity with which the journey is accomplished, right? So therefore, I can say that in this case, uh, t prime is equal to t over square root of 1 minus u squared over c squared is our formula. So here we have the distance modified as 40 into, this is the distance, right? So we can say that here it is 40 into 1 minus u squared over c squared by the velocity is u, right? So yeah, so using that we can try to solve this. So we can say that in this case, the distance is equal to 40 light years, which is getting contracted by this factor. So it is 1 minus u squared over c squared. So that is 40 into light year is light, the distance traveled by light in a year. So it is 3 into 10 power 8 into speed of light. This is meters per second. There are 3,600 seconds in an hour. There are 24 hours in a day, and there are 365 days in a year. That multiplied by this factor 1 minus u squared over c squared will give us, I don't take the direct value of light year, but I'm just trying to multiply. So I'm not directly taking the light year value. I'm plugging it in here first. 378,432 if I work out these numbers. And powers of 10 goes to 10 power 12 meters here. And then 1 minus u squared over c squared. And the time, for example, here in this case is 40 years. and that is 40 into 365 into 24 into 3600, and that is equal to 126,144 into 10 power 4. This is the time for the astronauts aboard the spaceship, right? So the velocity in this case u is equal to these two numbers here divided distance over time. So it is 378,432 into 10 power 12 over 126,144 10 power 8, sorry, 10 power 4. The numerator now gets 3 into 10 power 8. This is the number you would get. Times, of course, we have the square root here also, square root. So you get 1 minus u squared over c squared here as well. Now the question is, our expression is u over square root of 1 minus u squared over c squared from the previous this thing is equal to c, because here we have left hand side u, right hand side this is c times this. So your u by this is equal to c. So basically this equation, we are rearranging it here this way, isn't it? And that gives us, to the take u over c and do the square root, you will get u squared over c squared is equal to 1 minus u squared over c squared. That would give us 2u squared over c squared as 1. Therefore, u would be equal to c over square root of 2. Right? So that is the velocity. So that is the velocity of the spaceship. If they go at that velocity, then they would be able to maximum take 40 years to complete the journey. So therefore, I can conclude that it is 0.707 c. That is the speed. So the speed of the astronauts is 0.707 c. Right? So we can just write here u is equal to 0.70 c. Now the question is, how much time would elapse on Earth for this journey? Definitely it is going to be a dilated time on Earth, that is t prime is equal to t over this thing. So t is here 40 years. So 40 over square root of 1 minus u squared over c squared. We will plug this u value here, this value here, and then calculate a t prime, and we would find that that would be around 56.57 years for the total trip. That is 16.57 years or 16.5 years that we are added in the Earth's clock compared to the clock on the spaceship. That means compared to equally aged Earth-based astronauts, the astronauts who decided to sacrifice and travel that far for 40 years would gain about 16 years, 16.5 years, right? So that concludes that problem. Let's move on to a very interesting problem on pions here, right? A group of pi mesons supposed to be called pions are observed to travel with a speed of 0.8 c in a particle physics lab. How much is the Lorentz factor gamma for the pions? That's the first part of the question. That's very simple. Next part is, if the proper half-life of pions is 1.8 into 10 power minus 8 seconds, what is their half-life in lab frame? And then if the initial number of pions were 32,000, how many would remain after they have traveled a distance of 36 meters? How many would remain if we ignore the time dilation? That's the fourth part. Third part, we will consider the time dilation. The fourth, the D part, we would not consider the time dilation. Right? So here, why the question gives us the half-life of pions. That is why here the numbers are given, and we have to use the decay equation to solve this one, right? So let's do all the parts one by one. First part is very simple. We need gamma factor, that is 1 over square root of 1 minus u squared over c squared, where our u is given as 0.8c. So if you substitute u here, you get 0.64. So the gamma is going to be 1 over square root of 1 minus 0.64. That is 1 over square root of 0.36. That is 1 over 0.6. That is going to be 1.67. That is our gamma factor. So the first part is very straightforward. The next part, B, is if the proper half-life of pions is 1.8 into the power minus 8 seconds, that is the lifetime of pions in their own life, their own frame of reference, right? In its own frame, pion has this lifetime. But what is the lifetime or half-life in lab frame? Right, half-life cases, right? So again, time dilation expression will come to our rescue here. So T over square root of 1 minus u squared over c squared. If you want to indicate that it is a proper half-life, then it is T naught let us take the rotation. This is like gamma T naught, right? Gamma is 1.67, and therefore the 1.67 into the given half-life is 1.8 into 10 power minus 8 seconds. Therefore, the lifetime of pions in the lab frame is going to be 3 into 10 power minus 8 seconds. This is their lifetime in the lab frame. So it is extended, obviously, compared to in its own frame, dilated, right? Next is C part. If the initial number were 32, what would be the number? 32,000 rather, right? Initial number of pions were 32,000. How many would remain when they have traveled distance of 36 meters? So 36 meters, how many would remain? Right. So now what do? We have to um, first see how much distance they can travel at this time, isn't it? How much distance the pions would travel at this time. Distance traveled by the pions in this lifetime, that is in the lifetime of the lab frame, right? We can calculate that. At 0.8 c velocity, and this time 3 into 10 power minus 8 seconds, the distance that the pions would travel would be equal to 9 into 0.8. 9 into 0.8 is 7.2. These two terms will cancel anyway. So 7.2 meters only pions would be able to travel in their lifetime in lab frame. Now, 36 meters they have to travel, but so how many this thing will take? Half-lives would it take for this distance? That is the question, right? So half-lives, the number of half-lives for the pions to travel this 36 meters distance is 36 over 7.2. That would be 5 half-lives. So the pions would take 5 half-lives to reach this distance. And therefore, how many would have decayed during this time? Because if the initial number was 32,000, we have to see how many would decay. So let me go to this page. For that, what equation we have to use? We know that it is a radioactive decay equation. So the total number at the present time is equal to the initial number n naught times e power minus the decay constant lambda times t. Isn't it? This is the equation. In this case, the decay constant lambda would be, that 0.693 by the half-life t half. And our t is the total time elapsed, that is 5 half-lives. So that is 5 times t half. Okay, right. So we can plug in these numbers. Of course, the half-life is given as 1.8 into 10 power minus 8. But in this case, lambda times t when we do, we get 0.693 over t half multiplied by 5 t half. So effectively, these t halves will cancel, right? It doesn't matter what is the half-life in this particular case. So we get 0.693 times 5 as lambda t. So our equation in this case changes to again sorry, yeah, I write it here. um, N is equal to n naught e power minus lambda t, that is equal to 32,000 times e power minus 5 into 0.693, that is equal to 32,000 multiplied by e power minus 3.415, 465, 3.465. Then if you work out the numbers, the total number of this thing would be 32,000 times 0.0313. So how many pions will be left out therefore? Roughly 1,000 pions. The total number of pions that are left down would reduce from 32,000 to 5,000 or 5 half-lives. Right, so that is the conclusion for the part C. What about the final part here? How many would remain if we ignore the time dilation? If time dilation is ignored, with no time dilation, then what we would have calculated? We would have calculated the distance traveled in that case, the distance which we calculated earlier using the t prime, we have to calculate now using t. So it is ut, which is 0.8 into 3 into 10 power 8 times the actual given time, that is 1.8 into 10 power minus 8. Please recollect that in this original thing, here we have used ut prime for distance, and the time we use is t prime, which we calculated, and then we ended up getting 7.2 meters. But now we are using whatever is given in the question as the lifetime of pions in its own reference frame, right? So that is ut. So if we calculate the distance here, we end up getting only 4.32 meters. So in its own reference frame, pions would be able to travel only this distance during its half-life. Therefore, if you get the number of half-lives here in this case, just like before, number of lives, rather half-lives, number of half-lives is equal to 36 meters over 4.32 meters would be number of half-lives. That is about 8.5 half-lives, 8.57 roughly. Okay, so therefore, again we are doing the same equation. We have to do, that is the total number that would remain is equal to the total number that are originally there times e power minus lambda t, where lambda is equal to decay constant, which is 0.693 over t half, and t is equal to 8 half-life roughly, right? So 8.57, I'm ignoring even the 57, I'm taking only 8 half-lives, 8 t half. So lambda t therefore would be 0.693 into 8. So here The number that would remain capital N is equal to 32,000 was originally there times e power minus 0.693 times 8 minus of course. So if you work out the numbers, we get 32,000 times e power minus 5.544. And that would be equal to 32,000 into 3.911 into 10 power minus 3. I'm doing all the steps so that calculations are clear uh, to those who are starting to do some problems here, right? So that is the idea. It would be about 125 pions. If time dilation had not been there, then it would only be 125 pions. Whereas when time dilation is taken into account, we see that there would be about 1000 pions for this particular situation. So the number of pions is therefore reducing from 32 to 1000 rather than 125 because of time dilation. So here time dilation literally comes to the rescue of pions. Okay, right. So that sums up all the problems that we wanted to solve on the topic of time dilation in special relativity. Thanks for watching.